All right. Hello, everybody.
Hey.
I'm glad Zoom is working still. It's like, yay, every time it works, it's like fingers crossed. All right. I hope your other classes, I hope the technology is also going smoothly in your other classes. All right. So let's go ahead and get started. I think we've got a fair number of people online already, so that's great. The first thing I'd like to talk about is teams and repositories. So hopefully you've been talking and have some thoughts about your teams, and if so, great. If you could go ahead and send your team choices to myself and to Jenna by email, that'd be great. If you don't have a team yet, also send us an email saying you do not yet have a team, okay? Then we'll start looking at what the situation is and how we can form some more groups. Also, please get, once you have your team, go ahead and create a repo, okay? And it'd be great if you could do that today too. So just maybe pick one person on your team to make the repo and then send that along to us, okay? Or if you don't know how, then at the next office hour, I've got office hours right after the class today, and then Jenner has some office hours, I believe tomorrow, is that right, Jenner?
It is Monday and Wednesday.
Okay, you're Monday and Wednesday. Okay, and I think, what day am I? I forget what day I'm.
Tuesday, Thursday.
Tuesday, Thursday. Okay, so then on Monday, then you could get some office hour help with getting the repo created. Alrighty, so that's that. I think the next thing I wanted to talk about is to get into what is a definitional interpreter. Okay, or another way to say it is, what is the meaning of a programming language? Because we're going to be building these compilers, and the compilers need to sort of respect the language. Okay, they need to generate an executable that runs the program the way it's supposed to be run. And so, but the question is, well, what's the supposed to be? You know, how do you know what a program's supposed to do? And for this class, we're going to be using what's called definitional interpreters to communicate what a program is supposed to do. Okay. Before we get into that, just any questions about sort of administrative kind of things for the course, maybe left over from last time. Just give a little pause for that.
Yeah, I have a.
Yeah, go ahead, Sam.
So I know that Johnner said he wants just the one repo per team.
Mm-hmm.
Do you just want that to be like, do you prefer if it's an IU repo or if it's just through normal GitHub or anything like that?
I think we prefer normal GitHub. Is that right, Jenner?
There's no difference for me. Either way works.
Okay. Then we don't care.
Okay.
Yeah.
Whatever's good for you. If Jenner doesn't care, then I don't care.
Okay.
Actually, yeah, it doesn't make any difference to me either.
Right. I have a question. The one difference might be our, I'm not sure if Jeremy has it, but our usernames might be different in github.com and github.io. So there might be some, so it might be helpful for us to just be consistent about it for across all the groups. So why don't you just decide one, Jeremy, and just we can use.
Okay, let's because the most of the course material is already on github.com. Let's stick to github.com. Okay, just because that's where all of our stuff is, and it'll be
you can also publicly show off your compilers to everybody.
Yep.
I do have a question. I just got a message from Zach saying their team is composed of Kevin, Zach, Key, and Connor. So did we establish anything about team sizes?
2 to 4.
Okay, cool.
Yep. 2 to 4 is the number.
So 4 is good.
Yep, 4 is fine. Yep.
Okay.
I mean, if you really wanted to do 5, you could try to make an argument for that. But I feel like at some point you end up sort of too many cooks in the kitchen is the old phrase. You might actually take longer to do the assignment if you have too many people involved. Okay.
Will there be as much workload like to involve 5 people?
I mean, the projects are a lot of work.
Okay.
But I'm just not sure that 5 people, because with 5 people, I mean, you have to communicate a lot.
Yeah.
And the more people you have, the more you have to communicate, and so it may be harder with that many people. So that's my thinking and why I chose 2 to 4.
Yep.
Yep. Okay. All right. Okay, well then with that, maybe we'll go ahead and get started talking about definitional interpreters. Okay, I think I'll share my screen here in a second. Okay. All right. So what we're looking at here is the interpreter for the R. Oh, actually, I should be showing you the interpreter for R0 first. That was the interpreter for R1, which we haven't yet talked about. Okay, so this is the interpreter for R0, the language that we discussed last time, and it's one function. So per non-terminal in the grammar. Okay, so if you recall, there were 2 non-terminals in the grammar, one for expressions and one for the top level R0 program. Okay, and so we're going to have one function for each, and then because the expression grammar is recursive, this interpreter interp-exp function is also going to be recursive, and it's structurally recursive, just like that height function that we looked at last time, which means that it's going to do a pattern match on the abstract syntax tree, and it's going to have one clause for every item in the grammar, every right-hand side of the expression. And the pattern is going to, the pattern on each one of these is going to match what the grammar looks like. Okay. And then again, you have things like pattern variables to sort of pattern match against the either various information in the AST node or the children. So for example, here in this negation node, there's one child, and that's that E. That pattern variable E will match against the child. Okay. All right, so we're doing structural recursion, and this interpreter is meant to take a program and produce the output of running the program. Okay. So if your program is if it's just an integer, you're going to return that integer n. Okay. If you're doing a read, then what I'm defining here is that the behavior is that we then read from the input from the user, and this read here is the read for Racket, okay, not the read for R0, okay, and they're a little bit different, okay. The read for R0 only accepts numbers or integers, okay, in particular fixed nums, okay, integers within the appropriate range. So that's why this interpreter just doesn't return the result from doing a read. Instead, this interpreter checks that the result is a fixed num and then returns that. And then if it's not a fixed num, then the interpreter errors and says, hey, we expected an integer, okay? Now, these errors are an interesting point, okay? So when an interpreter returns a number, like let's say you interpret the number 42 and it produces 42, it's pretty clear that what your compiler should do. When you compile this program, it should also return 42, okay, produce the same output. But then we have to decide what to do when the interpreter errors. Like, what does that mean for your compiler? Does your compiler have to error too? In what way should it error? Okay. The convention that we're going to use in this course is that if the interpreter errors on a program, then your compiler can do whatever it wants with that program. Okay. It can do anything it wants at all. Okay. Whatever is most convenient. Okay. That's called undefined behavior. Okay. So and what that means in practice is that we're only going to test your programs on we're only going to test your compiler on programs that produce a result with the interpreter. Okay, we're not going to test them on programs that error. Okay, so if we're testing your compiler on some test suite and your compiler errors, and then we give you a bad grade, but then in fact the interpreter errors on that same program, you should come back to us and say, hey, no. The interpreter, all bets are off. The interpreter gave an error message on this program. It doesn't matter what my compiler does, okay? Now that convention is just for this class, okay? Let's say, a couple of years from now, you're a compiler engineer in some company, making big bucks, and you're implementing a particular language like, I don't know, Java or C++ or something. In these languages, oftentimes there are error conditions that are defined, and then your compiler needs to catch those errors and do some, and give a message to the programmer or do something, okay? There's actually, maybe you're doing exception handling. The language says you have to do exception handling, and then you're actually implementing some fairly sophisticated things to make sure that those exceptions propagate in the appropriate way. Okay, so that's the spiel about errors. Okay, let's move on. So the next one here is negation. So what we're doing here is we've got this recursive call to say, go ahead and interpret the sub-expression. And then once you've got that sub-expression, do a Racket's fixed num negation, okay, to that number. Or really, it turns out Racket doesn't have fixed num negation, it only has fixed num subtraction. So we're implementing negation by using subtract from 0, okay? So that's that. And then addition is sort of a similar situation here. We recursively interpret the two sub-expressions, and then we add them using fixed num addition. Okay. So that's what the interpreter for R0 looks like. And so, if you're asking, well, what should this program do? Well, the answer is run, interp R0 on the program, and you'll get an answer, and then your compiler should get the same answer. Okay. Any questions about this interpreter? Pause for a moment. Okay. I guess I want to draw a little picture to sort of hit home what I mean by correctness. Oh wait, what am I doing here? I'm trying to share. Oh no. It's sort of it's disorienting when you've got Zoom running about like what's your screen versus what's the shared screen. Oh no, and then trying to talk at the same time makes it even harder. Okay. There we go. Okay. So suppose you've got some program, we'll just call it P. Okay. When you run your compiler, so you do compile, it's going to become another program. Okay. Let's call it P prime. Okay. And maybe this initial program was in the language R0. I'll do a little. And maybe this P prime is in the X86 language, okay? So that's the compile step. And then you can run that X86 program like on your laptop or whatever. And then you get some number, okay? Maybe you get the number 42, okay? And then you can also take that original program P, and instead of compiling and then running it, you could send it through interp R0, okay? And you should get the same answer, okay? So you know your compiler is doing the right thing when it gets the same answer as interp R0. Okay, so this is what it means for your compiler to be correct. So a correct compiler. Okay, is one that satisfies this diagram. Okay. All right. Okay, the next thing I want to talk about is R1, the R1 language. And it's a lot like R0. It just builds on R0. So in terms of expressions, it still has integers and read, and negation and addition. But now it also has variables and let bindings. Hopefully I have the right number of parentheses there. And then at the top level, it's just an expression. Okay, so this is the concrete syntax for R1. Just noticed a typo. Okay, so let's look at an example here of an R1 program. And many of you will be familiar with these features because you're familiar with Racket, but I just want to, for maybe the few people who are less familiar, I want to go over what this let does. Okay, I guess maybe first of all, backing up, so var here is, for variable is any identifier. So it's going to be a string of letters. I think it has to start with an alphabetical letter and then like a lower uppercase letter, and then it can have numbers in it further down. Okay, so that's a variable. And then again we have, so let's look at this example now. So for this let here, looking at this let, we've got this variable x, and the idea is that x is going to be bound to the value of evaluating the right-hand side, okay? So when you add 12 and 20, you get 32, and so x, is going to be equal to 32 in the body, okay? So here's the body of the let is this region down here, okay? Maybe I'll do that highlight as well, okay? So this is the body here. And so in the body, the variable x can occur, and when it does occur in there, it's really going to have the value 32. Okay, so the result of this program is 10 plus 32. Okay, so that's 42. Okay. So and in terms of order evaluation, what a let does is it first evaluates the initializing expression, the right-hand side of the x, that is the 12 and 20. And then after that, it evaluates the body, the 10 plus x, and you get 42. Okay. So that's that. Any questions so far? Okay, let's do another example. Well, I'll do this one as a little mini quiz. Someone can tell me what the answer is here. All right. Does anyone know what this program evaluates to? Just FYI, I'm going to wait for someone to raise their hand.
Oh,
right.
yeah, there are some answers in the chat.
Oh, what's that? Oh, there's answers in the chat. I don't have the, unfortunately, I can't see the chat when I'm screen sharing. Thank you for that heads up.
They all say 42 though.
They all say 42. Awesome. Okay, thank you. That is correct. That's right. And so the little trick with this example that it sounds like many of you understand is that there's this overshadowing. Okay, so we have two binders for the same variable x, or two definitions of x, and then we have a use of x here, and the deal is that this x needs to refer to the sort of closest enclosing x, right? So that's that one. And then this x refers, there's only one x in scope for this one, and so it refers to the 32. Okay. So there's this shadowing behavior. Okay, and so your compilers will need to appropriately deal with this kind of shadowing. That you can have multiple definitions or really the way to think about it is that these two x's, they're really different variables that happen to have the same name. Think of them as like they're different people, but they both have the same name, Joe, okay? And if you're not careful, if you're just calling out, hey, Joe, you might get the wrong person, right? So you have to be careful about, which variable you're getting. And the idea is you're supposed to get whoever's closer, okay, by doing a traversal sort of up the program, okay? So those are the examples. Okay, so hopefully that gives you a good idea of what the R1 language is, okay? You've got integer arithmetic, You've got variables, let bindings, and you can get input, integer input from the user, and that's about it. One thing I should say is that in the very first time I taught this course, I did not have integer input. There was no read function in the R1 or R0 languages. And I had a very clever student who did not write a compiler really to solve to implement the language. Instead, what they did is they wrote an interpreter, and they could just run the interpreter on the program at sort of compile time, and then the executable that they produced was always like return 42, right? It basically didn't have to do anything. So the compiler was sort of just call the interpreter and you're done. But ever since then, I've included read in the languages so that you can't just interpret the program at compile time, because at compile time you don't have the input, right? So you've got to do something different, something smarter than just interpret the program. All right, so this is R1. Where we're headed to is X86. Oops. The X86 language. Okay. You may have heard by smart people that X86 is an ugly, terrible assembly language. And there's a little bit of truth to that. But thankfully, we don't have to use all of it. We're going to use a small part of it. And furthermore, we're going to use the X86 64, which is sort of this newer variant of X86 that makes it a little bit nicer in some ways. And so my feeling is that this variant of X86 isn't that bad to use as a compiler target. We're going to avoid some of the stickier stuff. We'll have to deal with a little bit of the ugliness, but not too bad. Okay, so what does this assembly language look like? Okay, well, from like a bird's eye view, an X86 program, is this sequence of instructions, where each one of these little squiggles is an instruction. Okay, we'll talk in a second about what that is. And what the computer does is it sort of does one instruction at a time and just sort of goes top to bottom executing instructions. Okay, so that's sort of a first high-level view of what's going on. We just have this sequence of instructions. So whereas like in R1, you could have like this giant syntax tree that's super wide and bushy and things like that. But for X86, it's just this sequence of instructions. Okay. Now, one thing that's kind of interesting is that this program is actually sitting inside the computer's memory. Okay, so I'm going to draw a big square here. This is, I'll label it memory. Okay, so this is inside of your computer, and there's a chunk of memory there that's dedicated to storing the program. Okay. Now, there's also something called the program counter that's sitting there in your computer. It's oftentimes abbreviated PC, and that points to the location where you're currently executing. Okay, so whatever is like the next instruction that's meant to be executed, the program counter is pointing at that instruction. Okay, and then inside of your computer, maybe I'll draw another big square here. So this one here is the whole computer. Okay, computer. And if you have studied architecture or multi-core computers, what I'm telling you right now is a gross simplification of what's really happening. Okay, and it's got enough detail, just enough detail for our purposes for implementing this compiler. Okay, so we get to ignore a lot of the other details, things like caches. Virtual memory, all this stuff, we get to ignore all that for now. Okay, so we've got a program counter, we've got our memory. We also have registers. Okay, registers. And these are a lot like variables, except, right, so you can think of them as little boxes where you can put stuff. but they have funny names, okay, like RAX or RSP or RBP or RSI, okay? And there's only 16 of them, okay? I think I probably already said that before, but it's kind of an important point. Your R1 program could have 1 million variables in it, but this computer only has 16 registers, okay? And later on, we're going to try to put variables into registers, but they're not all going to fit all the time, okay? So that's going to be a challenge. Okay, so all right, then, so that's, the next thing I want to say is that the rest of your memory is usually divided up into a couple different parts. There's the heap and the stack, okay? Now the heap is a place where you can say, hey, operating system, give me a chunk of memory, and then you can keep it for as long as you want, and then when you're done with it, you can give it back to the operating system, okay? So you can, as a program, you can ask for chunks, and you need to remember, you know, where they are. They've got addresses. And then later on, you can be like, okay, I don't need that anymore. You can give it back to the operating system, okay? We're not going to need to use the heap for this first assignment. We won't start using the heap until we start talking about tuples, okay? Which, you know, further on down the road here. The stack, we will have to talk about sooner than later. How many of you are familiar with what happens when you do procedure calls, and especially recursive procedure calls, and what's called the procedure call stack? Some hands, some not hands. Okay. Basically, what happens is, well, actually, let's say you have a recursive function. Let me think. Should I just do, I guess we could talk about the interpreter, in fact. That's a recursive function. But maybe not the best example. I guess I want to talk at sort of a lower level of abstraction. So maybe let's say we had a C function, like void f takes integer x, and then you had something like if, you know, x equals 0, return else, let's say return f of x minus 1. Okay, so we've got this recursive function. Okay, and so then let's say we call f with like 3. Okay, so we have this function call f of 3. So what's going to happen when you do that function call, right? We're going to jump up into this function, and we're going to have, you know, x equal to 3 as we're executing along. So we'll, you know, evaluate this. If, is it 0? No. Okay, call f again. This time we're calling f with 2, okay? And so now x is going to be equal to 2, and we need to go and execute that function again, okay? And then let's fast forward to when we're done, okay? Let's say we're done executing f of 2, and we're returning, oh, I shouldn't have had a return statement. Where do we return to? And actually, maybe just for fun, let's go like this, x plus, okay? Let's change this to a return with an integer there. Okay. When we return back to the, you know, the f of 3 context, maybe put an x, maybe an x here too. So we call the f with f of 2, right? And then now we're coming back and we've got a result. Okay, whatever that is. And we need x, we need to use x still. And x was 3, right? It should still be 3. Where in the computer do we know that x is 3, right? I mean, was it 2? Was it 3? Like, does x change? What's going on? Okay, so really what's going on is that what's happening is we're using the stack, and that every time you do a function call, I can never remember whether this goes up or down. I think it says it in the book. I'm pretty sure it goes down. So every time you do a function call, you create a frame, okay? And in that frame, you can store the values of the local variables, okay? So here's a call to F. Maybe I'll label this as, okay, we had a call to F. There's a frame for it. And then when we call F with 2, we're going to create another frame on the stack. Okay, so this is another call to F, but now X is equal to 2. But I can't draw here. And then, then we call F again with X equal 1, and then we call F again with X equals 0. Right, and at that point, it just immediately returns, and then as you're returning from these function calls, you're popping back off the stack. And so these are each of these is getting popped back up until nothing's on the stack anymore, okay? So these frames sort of literally stack up, you push and you push and you pop them back off. Okay, just like you learned about stacks in the data structures course. Okay. So indeed, there is a stack, a piece of memory dedicated to the stack inside of the computer. And in fact, we're going to use, there's 2 registers down here, the RSP and the RBP, that we're going to use to keep track of the stack. And in fact, the RSP, SP stands for stack pointer, and that always points to the sort of the last thing that was added to the stack, or maybe or the next empty slot maybe for the stack. Okay, and then the RBP is always going to point to the beginning of the frame, so it helps you figure out where you can find your local variables for a function. Okay. Okay, so that's what the computer looks like, and this idea about what the stack is doing. We won't have to do very much with the stack, thankfully. The only thing we have to be able to do is call a function that we've already written in C to do the reading, okay? And that's about it. Okay, the next thing we're going to do is we're going to talk about the actual particular instructions and what they look like in X86. Though, maybe pause for a second. Any questions so far about this sort of view of an X86 machine running? Any questions? And Jenna, if you see someone on the chat putting up a hand or a question, please let me know.
Yeah, I'm looking at it.
Cool, thank you. All right, so it sounds like we're good. Yes. All right, so then the next thing we should talk about is the actual instructions. Okay, so I can go ahead and do the grammar here. So oops, I keep forgetting I'm in highlight mode. So an instruction, so we've got things like an add instruction, add q. It takes 2 arguments. And then we've got other ones like neg q, has 1 argument. Move q, which has 2 arguments. Call q, push q, arg, and pop q, arg, and then ret q. Okay, so that's a small sampling of X86 instructions, and then we need to know what this arg non-terminal is. So an arg is either an integer, so it's the $ followed by, an integer, or it's a % followed by the name of a register, or it could be an integer parentheses % name of register. Okay, and what this does is it says, give me the value from a register and then add that integer to it. Or the integer could be negative too. It could be subtract. Okay, so it's oftentimes this is called offsetting. And typically what's going on is that maybe the register holds an address in it, and then you're adding or subtracting with respect to that address. Okay, right, and then the registers, again, these are the register names are things like RSP, RBP, RSI, RDI, RAX, RBX, RCX, all the way up to RDX. And then there's R8, and then all the way up to, oh gosh, I forget how high it goes. At least to R14, I think. Maybe higher, maybe so. Anyways. Okay.
I think 15. 15 is there too.
Cool.
There should be 16 total, right?
Yeah. Okay, so those are the registers. Okay, so let's talk a little bit about now the semantics of what these things do. Okay. So for example, let's talk about the add instruction. Okay. Now, with a lot of these 2-argument instructions, there's one argument that's called the source, and another argument that's the destination. Okay, so the first one's the source, the second one's the destination. So what add does is it reads from the source and it reads from the destination, and then does the addition, and then puts the result back in the destination. Okay. So if you're familiar, so let's say we had like, oh, I don't know, add Q, RAX, RDI. If you're familiar with like C++ or C or something, this is sort of like saying RDI plus equals RAX. Okay, it's this in-place update to the destination. Okay, so that's just a rough analogy. Okay, okay. What about? And so this idea of doing sort of updates in place is going to be a common theme in the X86 instruction set. So, for example, with the neg instruction, that's going to read from the argument and then do the negation of it, and then write the result back to the same spot. Okay. Move, what that does is it reads from the source and then just puts the result into the destination. So that's a fairly simple instruction. Okay. Now I should talk a little bit about these arguments, a little bit more about these arguments. So there's some funny restrictions on the arguments in X86. The argument here, when you're using this style argument, that's going to be either as the source or the destination. That's going to be, you're going to memory. Okay, you're reading or writing from memory at the address specified by the address in the register plus its offset. Okay, so there's no like, if you've seen like a RISC style architecture, you have like load and store instructions. You don't see that here in X86. Instead, you just have these memory style arguments. Okay, and then furthermore, there's a restriction that you can only have one memory argument per instruction. Okay, so let's say you're doing an add. Maybe the destination might be a memory location, but then the source needs to be a register or an integer. Okay. One other piece of terminology, when we're this just is sort of goes way back historically, that when you're talking about an integer being part of the instruction, that's called an immediate value, okay? Because it's actually encoded in the instruction, right? So like if you're looking at, you know, your computer's memory, there's some chunk of the instruction there that's dedicated to storing that integer, okay? So that's called an immediate value. Okay. All right, the call queue instruction. Okay, moving on down. The label is going to be the label for a function, sort of at the x86 level. In some sense, it's sort of weird at x86. 86 sort of gets the idea of a function because it has like a call instruction. But on the other hand, like all an instruction is really, I mean, all a function is really a label of a particular address in memory, okay? So like you have this, you know, long list of instructions in memory, and maybe this chunk here is a particular function, and there's a label at the beginning of it that you can use to say, oh, I want to call that function, which really is just saying I want to jump to the beginning of that, you know, that spot in memory where that function is. And then the next instruction I want to talk about down here is the ret queue instruction. And that's how you say, hey, I'm done with the current function. Please pop the current frame. And well, it doesn't do everything for you. You will have to do some of the work of popping the frame ourselves, but it does figure out where the part of the frame is the address of where the function was that you came from, and the ret queue instruction reads that and then jumps you back to the right spot from where you came. Okay. All right, so that's function calls, and then and we'll be talking in more detail later about those. Then there's also this push queue and pop queue. That's for adding and removing things from the stack. Okay. And it's just adding one sort of 64-bit value onto the stack or popping it back off. Okay, so that's what instructions look like. And then the grammar for a whole program, let's call it prog. So literally, it's really nothing more than like I said, a function is just a label, really. So you just have a label. You need a main function, so the operating system knows that's where it's going to jump into your executable and start executing the main function. And then it's just a sequence of instructions after that label. And then this little extra thing here is saying that the main function is a global, and that means it's sort of visible from outside this program so that the operating system can call it. Okay. So let's look at a little example x86 program. So let's look at an x86 program that does the same thing as this very simple R1 program that just adds 10 and 32, okay? So we're gonna have global main, move Q 10 into RAX, add Q 32 to RAX, move Q RAX into RDI, and I'll kind of walk through these instructions and kind of describe what's happening in a moment. Okay. So what this little X86 program is doing is it starts out by putting 10 into RAX. So we have this RAX register over here, and it has 10 in it. So that's the first instruction. And then the next thing we're going to do is the add queue. That's going to add 32 to whatever is already in RAX. So now we're going to have 42 there. Okay. So that's that instruction is done. Oh yeah, and I should mention that like, right, so X86, like the default thing is just to go one instruction after the next. There are, other instructions. So there's like the call instruction. There's also jump instructions that will jump you to other places. But the default is you just keep following through to the next instruction. Okay, the next thing is we move RAX to RDI. Okay, so there's another register over here, RDI, and that move instruction is going to copy the contents of RAX into RDI. Okay, so that's that. The reason why we did that is that we're about to call this print int function. Imagine that maybe I've implemented that in C in a different file or something. That function is, there's something called a calling convention, which is all about, well, part of it is about when you call a function, where do you expect the arguments to the function to live, okay? And so it turns out that print int is expecting its argument in the RDI register, okay? So whereas RAX, we were just using that internally inside of this main function to sort of as a scratch space, but we need to put that, we want to print 42, so we better put it where the print int function is expecting to find it, right? As, where it's expecting an argument. So that's why we put it in RDI. Okay, so we go execute that function, and then it finally finishes and returns back. Okay, and when it returns, that return address is going to bring us back to this move queue, and we're going to put 0 into RAX. So that puts 0 back in here, and then we're going to do, and then that's done, and then we're going to do the ret queue, which means we're going to return from this function. And one of the other parts about the calling convention is that the return value of a function is usually, as long as the return value is small enough, which it will be in this class, the return value is always in RAX. Okay, so that's how you return values from a function, is you put that value into RAX, and then whoever called you can look in RAX and access the result. Okay, and so what we're doing here is we're putting 0 into RAX because the operating system is expecting an error code in the return value of our main function, and a 0 error code means that we finished normally. Okay. Actually, we're gonna use the return value from our main to actually be the result of the program. It turns out it's just sort of convenient to structure it that way. So that's going to be a little bit odd. Like, let's say this program, actually what this program would really do, like let's say you're wanting to turn this in for your compiler, you would actually want to ditch, actually you could ditch all of these instructions and just add Q into RAX and then do a return Q, and that would be fine. You've got the results of the program in the RAX register. Okay.
Can I ask a question real quick?
Absolutely.
So here where you're at the end, you're moving 0 into RAX and then returning. I guess I'm kind of confused as how that would be the same if you did all of the work in RAX and you got the 42 and then just returned, right? Because
I guess what I'm saying is like this program I've written here is just sort of an example program that like prints 42. But when you're actually generating code inside your compiler, like let's say like, next week you put this program into your compiler, and then what should the actual x86 that you get out from that? And what I'm saying is that it should be global main, main, And or I mean, you could do something more complicated, but if it looked like the following, that would be fine, right? So you'd have the move queue of 10 into RAX, and then add queue, 32 RAX, and then ret queue, right? So that would be a perfectly good solution for the first assignment for this particular program. Okay. Did that clear up your question, or did I slightly misunderstand your question?
No, yeah, I think that makes sense.
Okay, cool. And I mean, there's other solutions that would be perfectly fine. This one's a particularly simple one, but you could, you could have something like move q 10 into a memory location. So maybe 8 RBP. So this means you're using the stack as part of your, and then maybe your add queue, 32 to that same stack location. And then now we need to get that stack location into our RAX. So then you'd go from that stack location into RAX and then ret queue. Okay. So actually, this first assignment, we're not going to be using registers very much. We're not going to map variables to registers. So your solution will probably look more like the one on the right, where you're actually using, because what'll happen is like this program will really turn into something like, well, maybe I'm trying to get ahead of myself, but yeah, we're gonna be using the stack for any variables that we end up introducing. So, all right. Any other questions about X86? The next thing we're going to do is talk about sort of compare and contrast X86 versus R1. But any questions about X86? Okay, so now comes the hard part. We need to compile R1 programs into X86 programs. That is, we have to write a program that just automatically takes any R1 program, anything that satisfies the R1 grammar, and turn it into an X86 program. Okay. Well, anything that satisfies the grammar and runs without error on the interpreter. Okay. So what are some of the differences between, right? And so so the differences, like our compiler needs to handle all the differences, right? Our compiler needs to sort of like, well, when something about R1 is different than X86, it needs to sort of do something to sort of bridge that difference, okay? So what are the differences between these two languages? Maybe I'll scroll back to the grammar for X86. Maybe also in your mind, you should have the grammar for R1. What are some of the differences? And some of these differences are sort of, in some sense, sort of trivial. Like they're trivial to say or to notice, but maybe not so trivial to deal with in the compiler. So don't be afraid to say something that's obvious to you, okay? So go ahead and shoot if you notice any differences. Okay, maybe to help kick things started, I'm going to mention a difference, which is that on the R1 side, we have variables and shadowing. And on the other side, we have registers and addresses in memory. And these things are all uniquely named. Right, so when you say RAX, there's just one RAX register. Or when you say -8 offset off the RBP, that's just one particular location, at least at a given point in time. Right, so we're going to have to sort of get rid of variables and turn them into registers and addresses. And furthermore, the fact that they're shadowing, you could have variables with the same name, we need to sort of deal with that. Okay, so maybe can anyone brainstorm like what might we do to get sort of get rid of this shadowing issue?
Kind of do something like De Bruijn indices.
Okay. So basically the idea there, if you're not, for those of you who aren't familiar with De Bruijn indices, you know, instead of using names for variables, like the name X or Y or whatever, you're going to use some other system that is unique, okay? And what I'm going to suggest that we do for this class is that we go ahead and keep using names, but that we rename all the names to make sure they're unique, okay? So this will be the uniqueify pass, okay? There'll be a phase in your compiler called uniqueify, and it's going to sort of rename all the variables, making sure that each one is separate from the others, okay? All right, so that's one difference here. Other differences.
Add Q versus like plus.
Yeah, so we've got plus over here and add Q over there, and what's sort of different about them?
Plus can take, well, I mean, it can kind of take a variable or an expression, but add Q only takes register name.
Yeah, so it has sort of arbitrary sub-expressions as arguments, whereas the add Q, the args on the add Q are either, you know, let's call them atomic, okay? Atomic args, right? It's just a number, you know, an integer or a register name, but it can't be like this big chunk of computation, right? Or big expression. It's just this one atomic little thing, okay? So that's a really good point. So what could we do to get from this world of arbitrarily large sub-expressions down to a world where our operations just are taking atomic things? Anyone have some thoughts about that? I mean, sometimes, I don't know if you've ever been writing a program maybe in Racket or C or whatever, and you had some kind of fairly large expression, and it was just hard to read. And so you wanted to make that expression you wanted to break it up into smaller pieces. How did you do that? What kind of refactoring step could you take to make that code maybe a little bit more readable?
Have like multiple lets and assigning the expression to different lets.
Yeah, so you take some sub-expression and then pull it out and put it in a temporary variable with like a let binding or whatever. Yep. So you create these temporary variables, assign them there, and then you can then use those variables. And now you've made the main expression smaller because it's referring to a variable now instead of this big sub-expression. Yeah. So we're going to call this one remove complex opera star. Okay, this is a historical name. There's kind of a pun going on here. But the idea here is that a complex operand or an operator, the arguments to an expression, if they're complex, right, there's some arbitrarily large sub-expression, right? And we want to remove those and then just replace them with simple atomic expressions, okay? So let's remove complex opera star. Will be the name of that compiler pass. Very good. Any other differences between x86?
Is the x86 not recursive, the grammar? I don't remember.
Yeah, that's a good point. It is just a sequence of instructions. And it's, well, okay, and maybe let's think about that from a control flow perspective, okay? Right, so in x86, the control flow is just sort of one instruction to the next. It's just very sequential kind of thing. What's the control flow in R1? What does the control flow look like? How do you know what gets evaluated next in R1?
Alice is saying in the chat, like a depth first traversal of the abstract syntax.
That's right. Yeah, so you've got this depth first, and it's doing sort of a left to right depth first traversal. Exactly. Whereas over here, the control flow is just sequential. Later on, when we'll add things like, it's sequential until we add things like jumps to different labels. And at that point, what we'll have, once we have sequential plus jumps, is we'll actually, it makes sense to think about this in terms of a control flow graph, conceptually. Okay. And so we're gonna need a way to go from this one style of control flow to the next. And so we basically need to sort of flatten out the control flow. We need to make it very explicit what's happening. And so this is going to be called explicate for explain, explicate control. Okay, so the idea is that we're going to have this going from this fairly complicated implicit control flow that's like this depth first traversal. We're going to redo the program such that it's just this very obvious where the control flow is sort of embedded in the syntax, with just a sequential sequence of instructions, and then maybe some jumps to labels as explicit edges in the control flow graph. Okay, so again, a very implicit control flow representation to super explicit in the syntax. Okay, so that's explicate control. Okay, I think we only have maybe one or two more differences I want to talk about. There's another difference that has to do with the operators. With, we have in R1 versus x86, you have plus over here and add q over here. The plus has two arguments, which are both input, and then it produces sort of an output, okay, a result from the expression. Whereas over with the add q, you've got a source and a destination, okay? So it's going to take a little bit of work to move from this world where we have two input arguments and an output, to a world where we have a source and a destination that gets updated in place, okay? So that's going to take some work. That's going to be what we're going to call select instructions. Or if you've heard the term instruction selection, it's sort of a classic part of compilers. That's going to handle this, this difference. And then there's one more thing. So we already talked about, we have variables versus registers, but here I want to sort of focus on a different aspect of that. Registers and memory. Okay, and what I want to focus on is that the number of registers is unbounded. Right? You could have a program with 1 million registers in it, okay, or 2 million or whatever, right? It's always going to be some finite number, but you have no idea what it's going to be. It could be huge, okay? So there's an unbounded number of variables. Now registers, we have 16 of these, and then we have an essentially unbounded amount of memory, okay? And that's not completely true, but it's true enough for this course, okay? And we need to decide, what to do with these variables, whether to put them in registers or put them in memory, okay? And in particular on the procedure call stack. And so basically we need to give each variable a home. So this is going to be called assign homes. And initially what we're going to do is we're just, like I said before, we're going to put all the variables into stack locations, okay? And then the next assignment is where we actually start doing register allocation, and we try to do a best effort of putting as many variables into registers as we can, though for some programs they're just going to have too many variables and we'll have to put some of those variables in stack locations, okay, in memory. Okay, but we'll do a best effort, and there's some interesting algorithms for how you try to optimize and get as many variables into those registers as possible. All right, we're almost out of time here. I guess one of the last things I want to talk about is the order in which we do these compiler passes. Okay, it's sort of non-trivial to figure out what order they should go in. And there's not sort of like a unique solution. Like you could do things in different orders and maybe things would come out okay. And actually there's a particular challenging issue in what we've talked about so far, is that there's a dependency between instruction selection and register allocation, or the assigning homes part of the compiler. And it goes back to this issue of you can only have 2 memory locations per instruction. Okay, so let's say you had a plus XY in your R1 program, and maybe if you did register allocation first, you might end up in a situation where both X and Y end up on the stack, okay? And then now you can't just generate an add queue for, maybe it's -8 RBP, -16 RBP. That would be an illegal instruction, right? You're not allowed to have 2 memory accesses in the same instruction, right? So then you might be like, oh, well, maybe I should do instruction selection first and then register allocation, or vice versa. Or maybe you should iterate them. Okay, actually that's the sort of if you really want to produce really good code, you actually have to iterate these two processes. What we're going to do is we're going to do instruction selection first, and then register allocation, and then we may end up still in this situation here, and then we're going to have to patch that up, and we're going to reserve the RAX register for patching up problem instructions, and then sometimes we'll have to expand one instruction into like 2 or 3 instructions to deal with that problem. Okay. This isn't exactly what you do in a production compiler, but it makes our life way simpler by going in that route. And it's only a tiny bit slower. Okay, so that's sort of an interesting ordering issue. Maybe I'll let you think about what order these passes should be in. You can also read the textbook for an in-depth discussion, and then maybe next time I'll just do a quick summary of what order you need to do the passes in. Okay. Definitely start, definitely be reading the textbook chapter. It's probably a good idea to, maybe get a start on some of the easier passes, like maybe Uniquify. Get your feet wet and jump in there and start working on that. Next week, Tuesday, Thursday, we'll be going in more detail through the particular passes. And so if you've already started to take a look at some of those and started to play with them, then you may have questions for me. That would be great. And I can help clear up issues that you're having as you're implementing the compiler. Okay, so maybe one last thing I should point out is, and this is in the book, we talk about this, is that we've got not only do we have interpreters, not only are we giving you interpreters for the input language R0, R1, we also have interpreters for the intermediate languages, okay? There's this, as you read the book, you'll hear about this language C0. It's the C-like language. And then also the X86 language. We've got interpreters for those. And so you can run those interpreters. So like you don't even have to finish your compiler, right? You don't have to go all the way to X86. Instead, you could do like one pass and then run the interpreter and check to make sure that that pass is correct. So for example, let's say you write Uniquify. What you can do is you can run the interpreter on the input program, do Uniquify, and then run the same R1 interpreter on the output and make sure that your Uniquify is correct. And you can do that for like, a dozen programs, and you start to get some confidence that that your Uniquify pass is good. And I really encourage you doing it sort of one pass at a time, and make sure you've got it right before sort of stacking multiple passes together, and you get an error, and then you have no idea like where the error is. Is it in this pass or in that pass? And it gets harder to debug. Okay, Jen Air.
Sorry, I guess the important point, one important point about this is in the compiler passes, it is critical that you don't change the meaning of your program while you're transforming the program into different languages. So your source language, your source program, and all the way to X86 program should mean the same thing. Mm-hmm. So that those intermediate interpreters help to verify those steps, like help to verify that you're not changing the meaning of the program.
Right. So we had this picture earlier on about what it meant to be correct, and now what we're doing is we're seeing that like, we're actually have a whole sequence of transformations that are happening to this program before it finally gets to X86, and at each step, you can run all of these, and they should all be getting the same answer. Yeah, that's a really good point. Alrighty, I think we're out of time, so we'll sign off for now. If you have questions, feel free to post on Piazza. Also, if you're
about
on
the
Slack,
groups,
yes.
I found a functionality on Canvas that we can form groups there. I got an email from Zach, and I formed the group there. If let's do it this way. If you're not sure how to get into a group, or like you want to be assigned to a group, just send me a message on Canvas and maybe add a comment about like add a score from 0 to 10 on how confident are you in your racket skills, so that I will assign people to different groups and like try to have like some sort of nice distribution of racket experience across the groups.
Great, thank you, Engineer. Mm-hmm. All right. So I'll be signing off, and I'll be available for office hours after this over on that other Zoom meeting. All right. Ciao.
See you guys.